Hello everyone, this is review for the final exam. I will include in the announcement where to find the review for the final exam, which will be in the same folder as the final exam itself. I note that the final exam is comprehensive, but 50% of the final exam will come out of the last chapters that were not included in the previous three exams. The exam will be composed of multiple choice questions, and the source of the multiple choice questions is explained under multiple choice questions title. Then the other part of the exam is problem solving, and that's the part where you need to submit the work for. And in the study guide, it will explain what to expect in the problem solving part. Again, 50% of the exam will be out of the last chapters that were not covered in the past three exams. So make sure to go over the questions here in the review. I will share with you a few questions here to help you with problem solving. And let's start here with a question related to chapter 3 over vectors. Now, as with all problems, make sure that you solve the problem yourself first, then you may check the solution.
This is problem which has three vectors that we need to add. Now remember that the addition of vectors is different from addition of numbers. We cannot go and add 50 plus 40 plus 60 and write the answer as 140 meter per second. This would not work. The way vectors are added is by placing them tail to tip. I'll start here by showing the graphical method of adding vectors, which is not required in this course, but it will give you a good estimate of the magnitude and the direction of the resultant vectors. To add vectors graphically, we place them tip to tail, meaning we'll move the second vector so that its tail is placed on the tip of the first vector, and we'll do the same thing for the third vector. It doesn't matter which vector you start with, meaning if you add vector 1 to 2 to 3, it will be the same outcome as adding vector 3 to 1 to 2 and so on. So here vector 2, for example, if we move it from this position to this position, and we can move vectors as long as we are keeping the same magnitude and direction. So vector 2 will be somewhere here, and again I'm just doing a rough drawing. So this is vector 1, which is the 50. This is vector 2, which is the 40. I moved it from this position to this position. Then the same thing here for vector 3. Place it here, trying to keep the same length, which is magnitude, the same magnitude and the same direction. So this will be kind of vector 1, vector 2, vector 3. And the resultant vector, which is the vector that represents the sum of the three vectors, will be the vector that connects the tail of the first vector to the tip of the last vector. So this is the tail of the first vector. I'll connect it to the tip of the third vector. So somewhere here, kind of estimate of the length and the direction of the resultant vector. We expect that the resultant vector will be kind of smaller than any of the three vectors, and also its direction is in the third quadrant, somewhere in the third quadrant, kind of somewhere between 60 and maybe 90 degrees here in the third quadrant. So this will give us rough estimate about the magnitude and direction of the vector. So if our answer came out something like 80 or 90 meter per second, we know that we did something wrong, because according to this graphical method, the vector is smaller than any of the individual vectors. And also if we get it somewhere at an angle of, let's say the angle came out to be in the second or first quadrant, then we know we did something wrong. So this is just to verify our results. But again, you don't have to do this step. This is just kind of a way to predict what we expect. We are going to use a method called resolving into component method, which is basically resolving the vectors into components and then adding the x component. The sum of the x components will be the x component of the resultant vector, and we'll do the same thing for the y component. And then when we get the x and the y component of the resultant vector, we'll be able to tell which quadrant it is in, and also we'll be able to find the magnitude of the resultant vector by applying the Pythagorean theorem. So let's apply that. Okay, we can start by creating a table. In the first column, we'll include each vector's magnitude and direction. In the second column, we'll resolve each vector into its x component, and in the third column we'll resolve each vector into its y component. In the last column here, this will be the sum of the three vectors. So we'll get the x component of the resultant vector and the y component of the resultant vector components. Now the first vector is this vector here, it's 50 meters per second, and you can see it's lined up with the positive x direction, so it has 0 angle. So vector 1 here is 50 meters per second at an angle of 0 degrees. The second vector here is the 40 meters per second, and we can see here that it's in the third quadrant. We need to write the angle as a standard angle. We are given the related angle to be 40 degrees, and we know when the vector is in the second quadrant, the standard angle will be 180 minus 40, because it's from this point to this point is the standard angle for the second vector. We know from here all the way to the negative x is 180, so this angle will be 180 minus 40, which will give us 140 degrees. So this will be at an angle of 140 degrees with respect to the positive x-axis. The third vector is 60 meters per second, and it's at an angle of 180 plus 70, because it's in the third quadrant. The 60 meters per second is in the third quadrant, so we have to add 180 to the related angle. So 70 plus 180 will give you 250 degrees. So now we wrote the three vectors in the format of magnitude and direction. We'll go ahead and find the x component of each vector. Now for the 50 meters per second, the x component is 50, because the whole vector is an x component. It does not have a y component. The y component will be 0. So it's 50 meters per second, and this, of course, in the positive x direction. Y component is 0. And we can do the calculation here. You'll take 50 sine 0. 50 sine 0 will give you 0. While 50 cosine 0 for the x component, it will be 50 cosine 0. Cosine 0 is 1. So 50 times 1 will give you 50. For vector number 2, it will be 40 meters per second times cosine 140. Cosine 140 will give you negative 0.766. So the answer here will be negative 0.766 times 40, which will yield minus 30.64 meters per second. So that's the x component of the second vector. The y component of the second vector will be 40 meters per second times sine the angle 140. Sine 140 will give you positive 0.643. When you multiply it by 40, this will yield 25.71 meters per second. And notice here this is positive, while the x component is negative. And we expect that because the second vector, as you see here, is located in the second quadrant. So its projection on the x-axis will give you a negative vector, while its projection on the y-axis will give you a positive vector, because it will project in the positive y-axis. Now we'll do the same thing with the third vector. We'll find the x component by multiplying the magnitude of the vector by cosine the standard angle. So 60 cosine 250, which will yield negative 20.52. Cosine 250 will give you a negative 0.342. And again, guys, make sure that you set the calculator at the degree mode, not the radian mode. While the y component will be 60 meters per second sine the angle. Sine 250 will yield negative 0.940. When you multiply it by 60, this will yield negative 30.76. When you multiply it by 60, this will yield negative 56.38 meters per second. Notice here that the x component and the y component of the third vector are negative values. And we expect that because the third vector, as you see here, is in the third quadrant. So its x component will be in the negative x direction, and its y component will be in the negative y direction. Okay, since we have the x components of the three vectors and the y components of the three vectors, we'll go ahead and add them so that we get the x component of the resultant vector and the y component of the resultant vector. So now we are calculating the x component of the resultant vector. Let's call it Rx, and this is Ry. And now we'll add 50 to negative 30.64 to negative 20.52, and this will yield negative 1.16 meter per second, while the y component of the resultant vector will be negative 30.67 when you add the 25 to the negative 56. Notice here that we got negative value for the x component of the resultant vector and negative value of the y component. What does that tell us? This tells us that the vector is in the third quadrant, because in the third quadrant, the y component and the x component are negatives. You need to know that very well. In the first quadrant, the x and the y component are positive. In the second quadrant, the x component is negative, while the y component is positive. In the third quadrant, both x and y components are negative, and in the fourth quadrant, the x component is positive, while the y component is negative. So this is how you can tell in which quadrant the resultant vector is located, and this is very important in solving such problems. So now we can go ahead and calculate the direction of the vector and the magnitude of the vector. Let's start, for example, with the magnitude. The magnitude of the resultant vector, and we'll put it in absolute value, which indicates it's a magnitude, is equal to the square root of the sum of the square of the x component added to the y component. So this will be the square root of the negative 1.16 meter per second square, and of course when you square it, the negative will disappear, plus negative 30.67 squared, and I'll let you carry out the calculation here. So make sure you complete the calculation, make sure to add correctly. So this will enable us to get the magnitude of the resultant vector. Now, magnitude is not enough, we have to find the direction. So for the direction, we'll start first by finding the related angle of the resultant vector. So it will be the tangent inverse, as we learned, of the y component over the x component. And this will yield tangent inverse. And again, you don't have to include the signs, but anyway, if we included the signs anyway, they will cancel out, the negative will cancel out. But it will be 30.67, that's the y component, the negative 30.67 over the x component, which is negative 1.16 meter per second over meter per second. Of course, the units will cancel out, and the related angle will come out to be 87.83. So it's in the third quadrant and it's making an angle of 87.83 degrees. So this is the related angle. We need to find the standard angle. And we know to find the standard angle, we have to add 180 to the 87.83 since it's in the third quadrant. So theta, which is the standard angle, 180 degrees plus 87.83. And this will give us 267.83 degrees for the standard angle. So now we have the magnitude of the vector and we have the direction using the standard angle. So now we can write the vector quantity of the resultant, which will be whatever the magnitude here at this angle, which is 267.83 degrees. And this will be the answer here. And you can see we found that the vector is in the third quadrant as we expected when we did the graphical method. Alright, I hope you found this video educational. Thank you.
The next problem I would like to go over is from chapter 4 over projectile. Again, make sure that you solve the problem yourself first, then you can check the solution.
In this problem, we are given the initial velocity components, which include the x component of the velocity and the vertical component. The question is, how high is point P, which is the highest point the projectile will reach, above point Q? So we're asked to find this distance, ypq. So basically the initial point here is the point where the projectile was launched, and the final point here is point P. That's our final point. Now we know at the final point here, the velocity at point P in the y direction will be 0, because we know that at the highest point, the y component of the velocity will be 0. And of course, the acceleration is g. Now, in order to be able to find the displacement between P and Q, what we can do right now, since our initial point is the point where the projectile was launched and the final point is point P, we can use this information to find the vertical displacement from the launching point to point P, and let's call it y0p, meaning from point 0, because we are taking the origin of our coordinate at the launching point, to point P here. So we are going to find yp minus y0. This is y0p. And then after we find it, we can add it to the 20 meters, and this will give you the total height from point Q to point P. Okay, so the plan here is to find the displacement from the starting point to point P and then add 20 meters to it, and this will give us the total height between P and Q. So the displacement is the unknown, and we are given those values. Now if you look for equation that has the displacement and all the other information is given, of course here the time is not given, and we are looking into the y direction because we are asked to find the displacement in the y direction. So the equation in the y direction that will enable us to solve this problem is equation number 5. Since the time is not given, we have to use equation number 5. The y component of the velocity at point P squared is equal to v0y squared, which is the initial velocity in the y direction, minus 2 times the acceleration due to gravity times the displacement from point C to point P, so it's yp minus y0. Now we know the velocity in the y direction at point P, which is the highest point, is 0. So this is 0 squared equal to v0y, which is 96 meters per second, and this is squared, minus 2 times the acceleration due to gravity, 9.8 meters per second squared, times the unknown, which is yp minus y0. And now we solve for yp minus y0. So rearranging the equation, we'll have 96 meters per second all square, where we moved yp minus y0 to the other side. And this is divided by 2 times 9.8 meters per second square. And if you carry out the calculation, this will yield 470 meters. Now this is the displacement from y0 to yp, meaning it represents this displacement. This is the 470 meters, and as you see, the drawing is not to scale. But this is not the answer, because the question asks us to find the distance from point Q to point P. So we are talking about this vertical distance here, the whole thing here. So we have to add 20 meters to 470, and hence the displacement from Q to P will be 20 meters plus 470 meters, which will yield 490 meters.
Now, in the third problem in this review, we'll discuss a problem from chapter 7 and 8 over conservation of energy and how it's related to gravitational potential energy and also the elastic potential energy of a spring.
In this example, if you look at it carefully, you can see that it's composed of 2 stages. The first stage is the free fall, while the object is under the influence of gravity. And then the second stage, where the object will encounter the spring and apply force on it, causing it to be compressed. The problem asks us to find the spring constant, which is K. And hence, stage 2 is the most important part. Now, in both stages, the non-conservative forces is 0. Stage 1, the only influence is gravity, while in stage 2, the only force applied is the force by the spring. and both of those forces are conservative forces. Hence, the law of conservation of mechanical energy can be applied on both stages, stages 1 and stage 2. So now if we go ahead and apply the law of conservation of mechanical energy on stage 2, since we are interested in the spring, we are trying to find K, the initial potential energy will be 0 initially. The spring is at the equilibrium position, y equal to 0. And the final kinetic energy will be 0 because the spring will compress all the way, and whenever it reaches maximum displacement at negative uppercase y, the velocity is 0. So this is the initial velocity for stage 2, which is not given. And at this position we have the final velocity of stage 2, which we know will be 0. So now if we go ahead and replace kinetic energy by its equation 1/2 mv square, and potential energy, elastic potential energy, by its equation 1/2 k x square, we don't know k, and we know the displacement is 15 centimeters or 0.15 meter. This is all square. Kinetic energy is 1/2 mv square, and elastic potential energy, elastic, is 1/2 k delta y square in that case, because the change is in the y direction. Now notice here that we have two unknowns and one equation, so we cannot solve for k. We have to find the initial velocity for stage 2. Now notice that the initial velocity for stage 2 is the final velocity for stage 1. So we have to refer back to stage 1 to solve for its final velocity. Now again, for stage 1, since the work done by the non-conservative forces is 0, and that's because the only force is a conservative force, which is force of gravity, hence the initial potential energy, and here the initial potential energy will be the gravitational energy, plus the initial kinetic energy, is equal to the final gravitational potential energy plus the final kinetic energy. Now note here that this is the initial condition for stage 1, and this is the final condition for stage 1. Initially, the object is dropped from rest, so the kinetic energy is 0. Now in the final condition, it will reach 0 height, so the final potential energy is 0. And now we can go ahead and plug the numbers. The final velocity of stage 1 is the initial velocity for stage 2. So we're going to solve for V final here for stage 1. So the initial potential energy is mgh plus 0 equal to 0 plus the final kinetic energy, which is 1/2 mv final square. And we plug the values. The mass is 2.6 kilogram, g is 9.8 meter per second square. The height is 55 centimeter, we convert it to meters, so it's 0.55 meters. This is equal to the right hand side, which is 0 plus 1/2 mv square. M is 2.6 kilogram times the velocity square, and that's our unknown for stage 1. You can see here that 2.6 kilogram will cancel out on both sides of the equation, and we'll solve for V final square, which is equal to times 9.8 meter per second square times 0.55 meter, so this will yield 10.78 meter per second. So we'll take this value and substitute it for V initial square in stage 2. So plug it into stage 2 equation, replacing V initial square. Recall that the final velocity for stage 1 is the initial velocity for stage 2. So we have 1/2 2.6 kilogram times the initial velocity square, which is 10.78 meters square over second square, equal to 1/2 k x square, which is 0.15 meters square. Now if you solve for k, 10.78 times 2.60 times 1/2 will yield 14.014. If you multiply it by 2 and divide by 0.15 square, this will yield 1245.69 Newton per meter. If we round it up to 3 figures, this will be 1250 Newton per meter rounded up to 3 figures. And this will be the spring constant. Note that kilogram times meter square over second square is Newton, and then the meter will cancel out with the meter.
The last problem in this review is over chapter 15. Again, please make sure that you solve the problem yourself first, then check the solution.
Now let's try to find the speed of the blood in the unhealthy vessel and also the change in the pressure. So to solve the problem, since we have two unknowns, again we'll start with the continuity equation, and we can write A2 in terms of A1. A2 is 0.2 A1 or 1/5 of A1. So on the left hand side we have A1 V1, and on the right hand side we replace A2 by 0.200 A1 times V2, and you can see here A1 will cancel out, and hence V2 is 1 over 0.200 times V1. Since V1 is 50 centimeter per second, which is 0.5 meter per second, hence V2 will be 5 times 0.5, because 1 over 1/5 is 5, and this will yield 2.50 meter per second. So as you see here, the blood will increase its speed whenever it enters the low area vessel. Now in part B, we are asked to find the change in the pressure, delta P. And we know delta P is P2 minus P1. So now if you look at Bernoulli equation, which is P1 plus 1/2 the density of the fluid, in that case the blood, times the velocity in the first region square, this is equal to P2 plus 1/2 the density of the blood times its velocity in the second region square. And now we rearrange the equation to solve for P2 minus P1. So we can move P1 to the other side and then move 1/2 for P2 squared to the other side. So we have P2 minus P1 equal to 1/2 the density times V1 squared minus 1/2 the density times V2 squared. We can take 1/2 the density as a common factor. So P2 minus P1 is equal 1/2 the density times V1 squared minus V2 squared. Okay, and we can go ahead and plug the values. So P2 minus P1, P1/2 times the density of the blood, which is 1.06 times 10 to the power 3 kilogram per cubic meter, times V1 square, which is 0.5 square, minus V2 square, which is 2.5 square, and this is meter square over second square. And if you carry out the calculation, P2 minus P1 will come out to be negative because P1 is bigger than P2. It's negative 3.2 times 10 to the power 3 Pascal. What that tells us, this means that the blood pressure decreases. That's the meaning of negative here. The blood pressure decreases by this amount, by 3.2 times 10 to the power 3 Pascal when it enters the unhealthy vessel.